Okay, so my name is Mike Goelzer. I'm from Protocol Labs. We're the folks who did Filecoin. However, that's not what I'm going to be talking about tonight. I'm going to be talking about another project we're working on called Libp2p, which is our modular networking stack for peer-to-peer applications. So if you think about sort of like TCP/IP plus HTTP, if you think about that whole paradigm as kind of the networking stack of the centralized internet, then what we aspire to do with Libp2p is build an analogous thing for the decentralized internet. So let me talk a little bit more about what I mean by that. I think that any discussion of the internet has to start with its origins, which came out of research in the 1960s about how do you build networks that are so decentralized they can withstand nuclear war. And part of the reason why folks back then were concerned about that is because this is what communications infrastructure looked like. It was a lot of centralized offices, human beings physically connecting wires in order to complete a circuit and allow two people to talk. Now, this photo looks silly and anachronistic to us today, in 2018. But what I want to submit to you is that it's actually not entirely dissimilar from the internet that we know and love and use every day and depend on for life and death matters and business and so forth and all these things. You have, I'm not going to say a small number, but a moderate number of very large players, and they operate services that are primarily centralized, and the largest of them do have some redundancy. Google, for example, I'm sure has redundant copies of their applications spread across data centers geographically, but it's certainly nothing like the original vision of the internet, which was why can't every node on the network simply be an equal peer to every other node? So that's one challenge with the current internet. There are some other challenges going on right now that I think are a little less dramatic than nuclear war, but are no less important. So I'm just going to briefly run through a few of them. The first one is firewalls. There are a lot of firewalls on the internet that prevent two peers from being able to communicate with each other, even when they're both quote-unquote online. A second problem is, and a sort of related problem is network address translation. Almost every machine on the internet is behind some kind of NAT, and the consequence of that is that two peers can't really communicate with each other because they often don't know what their public IP address actually is, and it's not always trivial to determine what it is. Another challenge is high latency networks. So one of the founding goals of Protocol Labs is to enable interplanetary networks. So you could imagine an internet that spanned between here and the moon. Clearly, there are fundamental limits of nature that ensure that no matter what we discover in the future, there's always going to be a certain time lag, a certain relatively high latency to get data back and forth between the moon. And that's relatively close. Even here on Earth, though, we have relatively high latency networks in a lot of situations. There's many parts of the world that don't have good, reliable connectivity, or even when it works, it's fairly high latency. So I live in North Idaho. It's a very rural part of the United States. We don't always have great latency. Sometimes we don't have internet at all. So these kind of challenges are real. A few more challenges I'll just mention. What we call the mobile addressing problem, or the roaming problem. So when you take your phone and you move around geographically, you're moving from one network to another, and the IP address of your phone may change, which doesn't change the identity of your phone, right? It's still the same device. It still has the same public keys that it can use to sign content and authenticate itself. And yet somehow we give it a different identity in different places, and that's sort of completely arbitrary. The other one I'll just mention really briefly, innovation in networking protocols is extremely slow. It's on a decade timescale, and are legitimate reasons for that, right? We depend on the internet for life and death applications, so you don't just want to sort of willy-nilly change what is the size of a TCP header, that could have negative consequences. But at the same time, it makes it really hard to innovate. So all of these different challenges are ones that we encountered when we started building IPFS. Now, I'm not going to talk much about IPFS, but I'll just mention what it is for anyone who's not aware. This is the Interplanetary File System. It is a peer-to-peer file system that we at Protocol Labs built with the goal of having a fully peer-to-peer way of storing data and transporting data around and preserving it for archival reasons. And we confronted all of those problems I just talked about. We didn't confront nuclear war, but everything else that I just talked about, we confronted those problems. We did confront reliability. We confronted those problems when we developed IPFS. And so we wrote a lot of networking code for what we thought was a storage project. And after we had done that, we factored that out into Libp2p. I guess the animations were lost here, but because this is the PDF version. But anyway, we factored that out into Libp2p, and that's the project that I'm going to be presenting on right now. Libp2p basically, I think I described it at the beginning as a modular networking stack for peer-to-peer applications. So what I mean by that is we have a variety of building blocks that we offer, and you as an application developer can pick and choose which building blocks are useful to you. The blocks themselves are fairly opinionated. I'll try to expand upon that a little bit in a moment, but you know, you can use whichever ones are useful and ignore the rest of them. We have documentation. Oh, yeah. Yeah, sorry, I lost the animations here, but we have documentation. This was going to be a cool animation where more and more windows pop up. So it wasn't that great. But the point is, each of those building blocks I showed you has its own API, its own documentation. You know, what do you use it for? How do you use it? We also have example code. This is all from our JavaScript implementation, what I'm showing you right now. That's the one that I think is best documented at the moment. We also have a Go implementation and a Rust implementation, which is the one that the Polkadot folks are using. And we also have several community-supported implementations. So those JavaScript, Go, and Rust are just the three quote-unquote officially supported. Not that we really do anything per se to provide support. It's an open source project. But you know, this is sort of the three officially supported implementations. And then we have a variety of community implementations in languages like C, C++, PHP, C#. Anyway, what I want to say a little bit about, and then I will try to use the remaining couple minutes for questions, is what I mean by what some of these building blocks are. So, for example, we have an abstraction called, let me just see what else is in this. Well, here, let me come at it from this angle. Most of you are probably familiar with the OSI 7-layer model. This is what's taught in every sort of networking textbook since the late 1980s, I think. And the OSI model prescribes a very specific set of layers, and the idea is each layer sees just a black box below it. It doesn't know anything about what's going on below it. We have a different take, which is that components within the Libp2p networking stack actually span multiple layers in the OSI model, or basically they're defined by what their function is rather than arbitrarily sort of having different layers of abstraction and not allowing communication between them. So we have some blocks that span layers and some blocks that exist in one layer, and also some blocks that overlap with other parts. Now, the reason I mention this is just to try to introduce what some of these, I'm not going to talk through each of these, there isn't enough time, and probably also not enough interest, but I'll just mention a few of these. What we mean by transports is how do you establish a connection between two peers? So in the most common implementations of the OSI model, that tends to be something like TCP/IP. or UDP IP. Those are the two main ways to establish connections. We have a much broader interpretation. Like from our point of view, if I have a mobile phone and you have a mobile phone, and we both have Bluetooth radios, why can't we just communicate directly? Like, why do we have to go out to, use Facebook Messenger to send a message through some server and then, have your phone pull that server and bring it back down? Why can't we just exchange data directly over the Bluetooth protocol? You could make the same case about Wi-Fi. All of our phones have Wi-Fi radios. Why not just exchange data directly like that? So our conception of transports is very broad. And similarly, another example from the other side there would be something like network address translation, where because so many devices are behind NATs, we have to have services in the library that do NAT hole punching for you. Like, we don't want higher level application developers worrying about that. We just want to provide that as core functionality in the library. So I could talk about this whole thing for an hour or more, and I have done so. Okay. Yeah. Okay, so on the second question, unrelated to Filecoin, we have equity investors. I don't think we disclose information about exactly how much we've raised, so I don't want to give a direct answer, but this work is being funded by the equity investments that have gone into PL. Your first question was, sorry, it was too technical, and how is it related to Filecoin? Yeah. I would say mainly it's not. This is a yeah. So I would say mainly it is not related to Filecoin, in the sense that Filecoin is its own project. It has its own engineers, time frame, and so forth. We're pursuing this in the interest of bettering the open source world. However, right. This is so part of PL's mission is to do research, and that's a lot of our our equity investors came in understanding this, that we wanted to do research. So, well, yeah, I feel it is, but I also don't want people leaving the room with the wrong impression. So let me just close by kind of saying this. Um, this work is independent of the Filecoin work. However, IPFS uses Libp2p as a building block. So it uses a bunch of open source projects as building blocks. So in some sense, you could say this does feed into the IPFS effort. IPFS, of course, is the substrate for Filecoin. So I hope that clears up. But yeah, this is not a token talk. I'm sorry if you came here hoping to hear a token talk. That's not what this is about. So.
Other questions? Oh, Patrick, here we go.
Are you doing anything related to turn and like WebRTC and turn, basically when you can't hole punch?
Yeah. We favor, for hole punching, what we favor is the approach of having two nodes simultaneously send SYN packets to each other and open connections that way. We think it's the most reliable. It's the like 5-way handshake of TCP. You sound like you're familiar with this. So in the more detailed version of this talk, I usually go into some of the technical details like that. But yeah, we're exploring a lot of different ways to do hole punching. Yeah, it's a work in progress. Yeah.
Cool.
Questions for Mike and Libp2p? Oh, here we go.
Yeah, thanks. Libp2p is awesome. I'm really excited about all the projects that are adopting it. What I'm wondering is, for the projects that are going to use Kademlia for routing and like the DHT, would they all be sharing the same DHT, and are there any like network effects that come from that, or would they all be on separate DHTs?
Yeah, so right now, oh yeah, DHT is a distributed hash table. It's a common element of peer-to-peer systems. We use, so IPFS right now is the main user of Libp2p. IPFS has a single DHT, or a single set of, it has a single set of nodes that provide DHT lookups. But in theory, you could adopt Libp2p in your project and have your own DHT, like you're not in any way wedded to IPFS's. So that's kind of how we're thinking about that long term.
So like for some of the projects like Ethereum that are like thinking about switching to Libp2p, like would they be on their separate DHT, or would they like use IPLD or something to address like their blocks, for example, in the network?
Yeah, you'd have to ask that to the Ethereum folks. So Ethereum has two groups. There's the Ethereum 1 group that is considering adopting Libp2p as a replacement for DevP2p. There's also the Ethereum sharding team that is looking at Libp2p for a different set of uses. I think it would depend on what each team's requirements are, but in general, we don't see them as using the IPFS DHT. I don't think that that's, I think they would want to control that themselves. Yeah.
Cool. Thank you.
Okay, great. If there's no other questions, we're going to go. Oh, there's one more.
Thank you so much. Great talk. I'm curious, what are your favorite today's use case of Libp2p, and also what do you think are the best use cases for it that nobody's building around?
Yeah, you're asking favorite use cases, and okay, yeah. So there's a few. There's PurePad, which is something that we're developing. It's sort of like a collaborative editor like Google Docs, but completely decentralized. That's live. You can see that as purepad.io or something. You can find it in Google. There are also video streaming services that are building on top of Libp2p. One is called LivePeer. There's also another one called, I think of them as Parity, not to be confused with the Polkadot people, but Paritii. No, sorry, I think it's a Portuguese word, but I don't know how to pronounce it correctly because I'm an American, so you have to forgive me. But yeah, you can find both of those. So live video streaming seems like something very promising, and yeah, collaborative editing. I mean, it would be so awesome to have something like Google Docs that was not centralized and was not controlled by a single authority and was just you and the other people that you want to edit with controlling the data.
Okay,
Should we wrap
great.
it up?
Thanks so much, Mike.